Feel free at any point if you want to come off mute and ask a question, please do. I also have the chat shown, and so I can see when somebody posts something in the chat. So feel free to do that if you're more comfortable. So today I'm going to be going over, first I'm going to be finishing up decision trees, and I want to go over the hyperparameters one more time. We went over decision trees in the last session, but it's been a while, and hyperparameter tuning in these models is by far the hardest part of the models. And you really do have to understand what the hyperparameters do in order to understand how to tweak the models, because it often does make a pretty big difference tweaking these models. So I'm going to start there, and then I'm going to go into random forest and gradient boosted trees. To start off, I was mentioning this, but not everybody was on the phone. I use gradient boosted trees like when I go through a bunch of models. I would say 80% of the time is the most accurate model. It tends to be really good, and you'll see more of why that is the case as we go through. I would say random forest is the number 2 on my list that that would be the second most common one that I pick. So it's usually you're able to, if something is predictable, one of them works pretty well. So I also use them for feature selection. Just in general, if you're working with big data, it's very difficult to do like SHAP values sometimes. It depends on your data size. SHAP values are used for feature selection. But if you're using big data, a great way to do it is random forest and gradient boosted trees, because they create feature importance as they train. So you don't have to use so much compute power to basically take one feature out, see how the model does, and then put it back in for every single feature. So I'm going to be focusing more on that in the next class, so that's coming. But right now I'm going to go through the concepts. But I did want to give you guys an overview of how these would be used on the job. So just to recap, I know some of you are new. So we went over decision trees in the last class. I think somebody's unmuted, so you want to mute. So hold on, I'll mute you. All right. So we went over decision trees in the last class. Decision trees are great because they're simple, and you can have a really nice visual to show a client that they'll understand. They tend to overfit very, very much. So they'll keep training and training and training, and then you'll have your models that are biased. So that's why we call them a weak learner decision trees, but they are the basis for gradient boosted trees and random forest. But I do want to go through and recap on the hyperparameters in decision trees, because they're the same for the most part in decision trees, random forest, and gradient boosted trees, with a couple of exceptions. So kind of going back and recapping, when you have a decision tree, hopefully I can pull up one of my visuals. So when I talk about a decision tree, it's something like this. We are trying to predict something. We make a prediction. In this case, salary. Our first node would be salary at least $50,000. And we're trying to predict, should I accept a new job offer? And then we decide yes or no, and then that moves us on to the next level of the decision tree. And then we answer another question, and then it moves us on to the next level of the decision tree until we get these green areas, which are nodes, where basically it gives us our prediction at the end. We either find a mean or a mode of that particular node to get that prediction from this model. So random forest and gradient boosted trees are built on hundreds or thousands of decision trees. We run multiple over and over and over again. Get more into that later, but this is what the model looks like. If you want to recap on how we decide which splits to do, I recommend going into my class. For those of you that have not been here before, I'm putting my class link into the chat. Feel free to go in there. I don't just teach this course. I teach a lot. I've taught courses and I'm teaching a lot of them. So all of that we've gone over will be available there. So when we're doing this, think decision trees, and we can now go and talk about hyperparameters. So hopefully most of you have know a little bit about machine learning. If you're a beginner, I highly recommend going back to the beginning of this class and watching it through. But when we're tweaking hyperparameters, we're basically tweaking the model and trying to, in the most cases, try to find the best balance between over and underfitting your model. So if you say run a decision tree with 500 levels, which can happen, it's not the right way to do it, it will basically memorize the training data. And it will not be generalizable to new data. So these hyperparameters in general really help to deal with that particular issue. The max depth is the one that's listed at the top here. Max depth is usually the one that makes the most difference, and my ending model usually includes it, either by itself or with another hyperparameter. It generally makes a big difference in model accuracy. It helps to control overfitting. So the maximum depth, or i.e. levels of a tree, so that is max depth. So you can say, if you set it as 5, your decision tree cannot have more than 5 levels. When I say levels, I mean this is 1 level, this is 2, this is 3, and this is 4. So my decision tree has 4 levels in this particular picture. So in general, I find that I usually vary max depth anywhere from 3 up to, I'd say, 20 when I'm tuning it. And you'll want to go and check multiple max depths or any of these hyperparameters and see how it does. The way I explained it to one of the people on my team is you usually see, like, I would go with the default, or I'd start down at 3. And then I'd train like 3, 5, 7, and 9, for instance. Let's just use that as an example. And usually you'll see an accuracy, as accuracy will increase, it will hit basically or near your optimal level. And then after that, you'll see the accuracy go down. So there's usually a curve. And then you're looking for that optimal level of accuracy or F-score or whatever you're looking at the top of that bell curve. That is the optimal level. When you see it decreasing on the other side, that means that you're probably, in this case, underfitting the model. So that it basically allows you to control that. So if you have a max depth of 3, it's gonna make it so that it controls overfitting, so it doesn't get too big. But if you have a really, really big decision tree, it's going to overfit and memorize your data.
I've got a question.
Mm-hmm.
Just to make sure I'm kind of following along here correctly, because this is the first time. I think I just made like a dummy tree like last week, and so this is the first time I've kind of engaged this model. Is max depth it's bounded by like the number of features you have, right? Or the number of the dimensionality of your data, right? Like you can't have a max depth. I mean, it wouldn't make sense really to have a max depth of like 9 with like 3 if you had like 3 or 4 features, because you couldn't build a tree that deep, right?
Correct. That's absolutely correct. That's a great question, actually. That's not an obvious question to ask. So usually in a decision tree, they only use a feature one time. So if it's used earlier in your tree, as you go down, it can't be used again. That's also a downside of decision trees, because basically the decisions you make up top, they may not be the best decisions for the tree overall, even if they're the best for that first initial split. So say if you use that one feature, now you can't go back. And you may not end up with the ideal end result because of that. So that's another reason why random forest and gradient boosted trees tend to do better. Does that answer your question?
Yeah, I think so. Yeah.
Awesome. That's a great question. So the next one is minimum samples per split. This is very similar, and it does a very similar thing to max depth. It controls overfitting. So you saw that each tree had like a split when it asked it a question, or it's usually a yes or no. So what this will do, if a new split, if you're making a split and you have to have above a certain number of samples at that time of that split. So then the observations in your data, if you set it as 10 and you have for that next split 9 samples, it's going to stop and go with the result that you had on the after the previous split. So it's another way to do something called early stopping. So you're stopping your model so it doesn't overfit. Very similar as minimum samples per leaf. I'm just going to keep coming back to this. Minimum samples per leaf. See, when you're talking about minimum samples per split, we're talking about the split here, the yes or no. And when you're talking about minimum samples per leaf, we're talking about our end nodes here. So if we set 5 as our minimum samples per leaf, if we get to a point where we make a split and there are, say, in one of your nodes, 4 samples, that means that it will go up to the previous level and stop your model. Again, an example of early stopping. So the fewer number in both of these cases, the lower that number, the more chance that you will overfit your model, because your nodes will have fewer values in it and it will memorize your model to a larger degree. Are there any questions about those? All right. So you can think of this one, minimum weighted fraction per leaf. This one, I'm just going to read the fraction of total samples required to be in a leaf node. If a sample weight is provided, it will give values in the numerator a higher weight if the sample weight is higher. So this is very similar. But this time we're looking at a fraction. So say 20% or 40%. But we also can apply something called sample weights. Sample weights, they help often when there's class imbalance. And you're going to see this throughout your career if you go into data science. So usually when you train a model, the model usually, no matter how you train it or all the hyperparameters you use, usually like you're either having false positives or false negatives. You usually don't do well on one side, either predicting the ones or predicting the zeros. And a way to deal with that is to set weights. So basically, if you are setting a sample weight that like giving the ones or a higher weight, then it will help you, it will help or give more weight to the ones that you're trying to predict versus those zeros. You can also weight based on, say, an example from my work for an auto company was we were trying to predict how much money somebody would spend in a dealership. So we knew that recency, how long ago they were into the dealership, was really important. Just that was business knowledge that they had and knew from descriptive statistics in the past. So in order to try to get my model to predict better on the ones, I actually gave higher weight to rows that had a shorter time since they had been into the dealership. So they was weighting those as being more important when I went in and trained my model. So that helps. It usually helps even out, and it will give more weight to those ones, and then it will predict ones better in your model. So that's a great example of why you have to have domain knowledge in whatever you're doing. So sample weights are actually probably the hardest one to understand. So they're easier to understand in like random forest and gradient boosted trees because you run it a bunch of times. But does that make sense? Hopefully with the example, it made a little bit more sense.
I had a question. So basically, so at this point, when doing the weighted fraction, it's important to understand or know the feature. Before you, is that what it is? Like you have to know the feature before you do the weighting. As in, like in your example, you knew already that lesser time or the time spent was important.
Yes.
Okay.
Yeah, that's usually domain knowledge is required there.
Okay, that's domain. So that's not like a separate algorithm that you ran that told you this. It's
no.
Okay.
Yeah, it was. I went and talked. So there's a person on my team at work that has worked at my job for 15 years. Okay. And she just knows everything. She's one of those people. So, and this is, I find a mistake made by data scientists is that they come in and they don't try to understand what they're doing and what they're trying to predict. And that's a big mistake. And this is a great example why. And I think that this is useful because this is a problem we're going to run into. But in general, I was not, things didn't look right because I was getting those ones wrong. So I went and we actually did a weight based on two features in that case. It was the amount spent in the dealership, and it was the recency in that case. So we knew if we were predicting how many cars they would want to buy, spending money in the dealership made it more likely that they would buy more cars because they were more loyal to the brand. And then that recency value. And that's the part that's hard, is finding out what to set the weights as. So in this case, when they were high on both of those features, I set the weight to like 1.4 or something like that. And then if they were high on one of them, I kept it at 1. And if they were high on none of them, I kept the weight at 0.6, for instance. And then I tried and I tweaked them up and down and looked at when my false positives and false negatives looked pretty similar. And then I stopped.
I see. Okay.
So it's a very big trial and error when you go through, but then it'll weight those values higher when you go through this process if they have, they're higher on those particular metrics.
Okay, got it. Thanks, Kelsey. Appreciate it.
No problem. Yeah, that one is useful in a lot of different areas. It comes across, and if you ever do segmentation or clustering, they like K-means has in most packages a sample weight too. So that was a really interesting thing to do there. So they found that in our important groups, there weren't enough segments. So I increased the sample weights and it put smaller groups for my higher segments. So you're going to see that throughout your career, the sample weights, and they're very useful. If you see something going on based on stakeholder feedback, you can often tweak those weights and give them what they want, but have an accurate model, and your model might be more accurate after you use them. Awesome question. Any other questions about that one? I know it's a difficult one to understand. All right, so this one's pretty easy to understand. Maximum features, it basically will, in case of your decision tree, it'll keep going until, say, if you set max features of 7, it'll stop once it's used all 7 of your features. And that's another case of early stopping. If you have a smaller number of features, it's going to be less likely to overfit. If you have more, it's going to be more likely to overfit. So that one's pretty simple. Maximum number of leaf nodes. So I'm just going to come back to my example. These terminal nodes or leaf nodes, you'll hear them have a lot of different names. Basically, in this case, it can't have more than a certain number. So in this case, there are 4. So if I set the maximum number of leaf nodes at 3, it would have stopped up here. So because it has 4 here. So that's what that means. And finally, this one, if you weren't in my last class, I'm not going to go over the definition of impurity again. It's farther up in these slides, actually. But please feel free to go back to my class. But in order to decide where to split and what features to split on and where to put the cut points in a split, it looks at the impurity of all the different options on how to split your tree. Impurity tells basically how pure your nodes are. So it wants more 1s in one leaf than 0s, and more in another leaf, you might have more 0s than 1s. Basically, you don't want them spread out. You want them more similar in your different nodes, because that means you're predicting it better. If there's 50-50, that means your model isn't predicting very well, because it's going to take the mode or the mean. And if it's split in the middle, you're probably not getting your prediction right. So what this does is the minimum impurity decrease. So every time you go to another level of your decision tree, your impurity hopefully decreases. And when you make that split and you make those nodes more pure, this one makes it so once your impurity hits a certain level, it stops your model. This is the hardest one to tweak, I would say. And because there's not really a good cut point usually, so you have to try a really large variety of them. And I find that it, in general, is one of the least effective ones that you can tweak. I think part of it is because it's a little difficult to do. Is there any questions before I move on? So we're talking about decision trees, but we're also talking about random forest and gradient boosted trees. So I'm gonna zoom back out. Gradient boosted trees and random forests are examples of ensemble models. So ensemble models are taking those decision trees that we just talked about. They're called weak learners because in general, the models tend to overfit. And I'm going to give an example quickly. Hope. All right, I'm going to try to give an example of an overfitting decision tree, but I'm not teed up and ready to go. So an ensemble model takes those things that overfit or don't do very well on their own, and it trains hundreds, thousands, tens of them, depending on how many you tell it to do. And it does it multiple times and takes the insights basically from a lot of different decision trees and then gives you a more accurate prediction in most cases. So you can think of it as running something many times, and you don't even have to do just decision trees. You can actually do ensemble methods with any type of model by running it multiple times. There are different types of ensemble methods. First, bagging, and if you're in statistics, you will have heard this as bootstrapping. Bootstrapping is repeatedly running a model and taking the average of your results. So this is often used in simulation as well. So that's something that you may have heard of outside of the context of machine learning. Boosting, if you've never heard of machine learning, this one's going to be new to you. This builds models sequentially, and each model tries to further reduce the bias seen in previous models. So in the case of gradient boosted trees, I'm going to go into more detail, but it basically tries to predict the error that the previous decision tree left behind. Stacking is, this one is highly processing intensive, so I don't use it very often. But it means that you would run like 3 models, take those and then find a regression of the results of those models, or do a logistic regression of the results of those 3 models to get a final prediction. I've seen this more often in AutoML. AutoML programs use this. I've only really seen it when using Data Robot. So other than that, haven't really seen it before. Are there any questions about this? All right. I was able to pull over while I was talking about that, an example of an overfitted decision tree model. So I, on purpose, didn't do early stopping on my decision tree model just to show that how bad this is. So I let it go until it quit on me. I used the defaults of the decision trees, so didn't use a max step, didn't use any of that. I think I had somewhere around 40, 50 features in here, probably more actually. And then I fit this on all my features just so I could show what overfitting looks like. You can see here, look at my bar on the right, how many levels this decision tree has. It's ridiculous. So this was a very terrible model. You can look down here, the precision, and that was actually, you can look here. So my accuracy was only 65%. And I really had low precision here. So I, in this case, had a really terrible model, and it was overfitting for obvious reasons when you look at that. So that's an example of why the decision trees can't have to be tuned. So random forest, oh, go ahead. Is there a question? Okay. So random forest is an example of the bagging concept. So think bootstrapping. So random forest basically runs however many models you tell it to. It takes a random sample of the subset of your features. So it will take, say, seven out of your 10 features, randomly select 7 of them. If your max features is set as 7, and then it will run a decision tree. And then it will take a new subset of your features, run another decision tree, do it again and again and again and again. So then at the end, it makes an average, a simple average or a mode, depending on if it's a classification or regression problem, to pick the final prediction for across all of the decision trees. So the reason that this works, each tree has high variance. So if they're really short decision trees, like it cuts it off at 3 levels, for instance, this will decrease the variance and the overall bias of the model if you do this many times over. And it tends to be a very high performing model in general, not usually as good as gradient boosted trees, but it's usually pretty far up there. So an example here, just in general, is a sample with replacement. And always random forest samples with replacement. In this case, we say have a feature, we have original training data of 5. It will take a random sample of these and then move them on to each decision tree. And you can see dog is in there twice. So that comes back to here. It's taking a random subset of samples from your training data with replacement, and it's taking a random subset of features to create the model splits. So I think I missed that first piece the first time through. So it's not only just taking a random subset of your data, it's also taking a random subset of your features. So doing those two things. The random subset of features obviously is not with replacement because you can't do that. But this shows here that the row dog can be chosen twice in the same decision tree and put in there multiple times. And sometimes it wouldn't be in this case. So this just shows 3 bootstrap samples and 3 decision trees and how that would work. Are there any questions so far? All right. So for the most part, the decision tree hyperparameters that we just talked about, I think all of the decision trees ones apply to random forest. However, there are some additional ones that we have as well. So in this case, class weight, it's called something different here. So we're giving the class weight. We've already kind of talked about this. The number of estimators is often a really good one to tweak in random forests. So that's the number of trees in the forest. So how many decision trees does it actually sample? So as you increase this value, it can decrease overfitting because it's averaging more decision trees. But the training time goes way up. So if you have big data, it's going to take a lot longer. So the bootstrap is whether a subset of samples are used to create the trees. So you can use 100% of your samples, or you can use a subset like pulling 90% with replacement, like we just talked about. This decreases bias and tends to decrease overfitting if you would say take 70 or 90% of your samples. Class weight we've already talked about. And then final maximum samples. So this is the maximum number of samples used to train each decision tree. So this would be, and then I'm actually coming back and I'm wondering if the maximum samples, I actually think that this is the same as the bootstrap. So it's possible that I was going through and used 2 sets of documentation because the samples are the number of rows and you're picking a subset of samples here. I guess if you wanted to choose an integer, but this is very much the same thing in this case. So apologize for that mistake there. So now I'm going to show a little bit of, I'm not going to run these models because they do take quite a bit of time to go through and run, but I can show you the results and what happens when I tweak one of my hyperparameters. So I think random forest is a little bit farther down in the code here. Yes, so that is it. They start down here. So in this particular case, I started off with just the default. Scikit-learn does a pretty good job of choosing good defaults when you run the model. So I usually start off with just doing absolutely nothing. And every once in a while, it actually is the most accurate model when you do that. So you'll see here that in this case, I'm using a random forest classifier. In this particular case, if you haven't been to the class before, flip back real quick because I forgot to mention this. The data that we're using to in this particular class, we have a set of every substance abuse treatment that was publicly funded in the United States in 2018. I took a subset of that data so that it wouldn't take so long for the models to run. We're trying to predict which admissions were first-time admissions and which were repeat admissions, with the goal of trying to predict which individuals would be at high risk for relapse versus low risk for relapse coming into the substance abuse treatment center. So here, you'll see that I use random forest classifier in this case. You would use random forest regression if you're predicting a continuous variable. Here, where it's a 1 versus a 0. You'll find in most programming languages that you usually have to fit your model first. So I take this, basically, you can think of this as a shell. So I set my random forest classifier here, and now I'm pulling down that value that I set, or that shell, and then I use .fit. And then I'm using my training data. In this case, it was after feature selection, so it's my X train small. We're going to go over feature selection in the next class. And this here is specific to scikit-learn. It is setting it, NumPy is used, and this puts it into the correct data format to go into this model. Now, once you fit that, I take that object that I set for the fit, I move it down here, and then use it to make a prediction on my validation data set. So I have my training data set, and I think it's 60% or 70% of my data. I'll have 20% in a validation data set, and then I'll have maybe 10% in a holdout data set. So this is going to test the model on unseen data so that we can see on unseen data how our model performs. And then you end up with what is shown down here. I printed a description. It's called the classification report. That outputs, without you having to do any extra work, the precision, recall, F1 score, and support. I generally don't use support very often because there's not really good benchmarks to know if it's good or not. If you need a refresher on these, I believe that was 2 classes ago, we talked about precision, recall, and F1 score. F1 score is usually what I focus on because it's basically an average between precision and recall, meaning it's finding the balance between false positives and false negatives. So it's finding that middle, ideal middle, if it is, if it has a high F score. So in this case, you can see the accuracy, not very good, 69. And then the F score is 62, which is really bad. So for zeros, it was 62. So we are not predicting zeros very well. In this case, there's a lot of false. It would be, in this case, if we're getting it wrong here, it would be a false positive. If we're getting it wrong here, it would be a false negative. So it's by default predicting more ones in this case. So it's defaulting to those values. And you can see that down here in the confusion matrix as well. So we're seeing the true label here, the predicted label here. The darker is better. So it's predicting 2 or more. So those people who were actually on a second admission or more admission, we got those people right more often than we got the people who were first admission right. So that's why this is lighter here. And these are, in this case, we predicted a first admission, but it was really 2 or more admissions. So that would be a false negative. And down here, in this case, we would have predicted a first admission when it was actually a 2 or more admissions. So in that case, it was a false negative. So that was my default model. So now I wanted to change the number of estimators. And this is the number of decision trees that it runs, or the decision trees in your forest. So this one is going to have a very big difference on training time. So I did 200, 300, and 350 in this case. Then I printed and I ran it in a loop and printed this out. So you can see here that the number of estimators did not change the metrics at any of them really at all. So the number of estimators, I can pretty much throw that out. It's not going to help me. And that's pretty common. Number of estimators in this particular model doesn't usually change it much. Now, minimum samples per split. We'll remember that as it stops if the next split leaves it with too many samples. So in this case, it would be each split has to have at least 5 samples for it to occur. Come down here, and you will see that it's actually increasing here, but not by very much. So we're seeing the accuracy increase, but as I go up, it's only increasing a little bit. So that indicates to me as a data scientist, this probably isn't the right thing to tweak. It's not really changing my model much. Minimum impurity decrease. This one is hard to tweak, and in general, it's hard to get right. So it's basically as the impurity gets smaller, your model's getting better, and it has to hit a certain level. Once it hits a certain level, it can't keep going. Down here, we're seeing that as I increase that number, it's getting much, much worse. Our model is tanking basically as it goes up. And even with a small impurity decrease limit, it's still not doing very well. So this is also probably not our best option. Now we have our max features. So subsetting the number of features that we use. And I'm using it in combination with minimum samples per split just to see what happens. So come down here, see the results. So we're seeing that bell curve effect. You remember, so it's not very drastic in this case, but we're starting off lower. We go up, we are peaking here, and then it goes back down. So we're seeing that this is the ideal number. So a max features of 7 and minimum samples per split as 12. And the number of estimators, in this case, I kept at 300 because that was the best that performed up at the top. So this one now going through the minimum samples per split, and this would be a weight. So this is another way to set it, the class weight. So we are basically giving more weight to those 1s versus 0s. So there is a difference between like what we talked about earlier, and then this would be if you're giving weight to a certain class. So if it gets the 1, we would weight the trees more when they had 1s versus 0s. And that is different from the sample weight that we talked about earlier in the previous model. Down here, we're seeing that we are doing well with a weight for the 0s of 1.5. This is going to help when we're trying to get those false negatives down. And in this case, we're hitting a 72% accuracy. And this goes into the holdout data set with our final models. Are there any questions about random forests before I move on to gradient boosted trees? Okay. Question about the data. Do you know if it accounts for voluntary versus forced admissions? Yes, there is a feature in the data that says how they were admitted, whether it was like punitive by a court. That actually tends to be if they were forcibly admitted by a court, they tend to be more likely to be a later admission. And I can go up to the top here and show this is all data cleaning. Can pull in the data columns. So you'd be able to see here whether they have alcohol in their system, their race, whether they smoke, the number of arrests that they've had in the past, and methadone use. And there, I may have taken out, oh no, here. So P-source is how they were referred. So an employer referral, court referral, community referral, so on and so forth. Random, okay. All right, I think that was the only other question in the chat. Right. Now, gradient boosted trees. It's the one that works really, really well in most cases. So most often, this is my best model. I'm going to start with the gradient boosted regressor and then talk about the classifier because it's a little bit different. So the gradient boosted regressor, we're starting off. So it fits one decision tree to start off. And it makes a prediction in this case. And then it will, in its final nodes, find the mean of every value that's in the final node and they'll find the mean of that node. And that is the predicted value. And then it will find the residual or the error in that first prediction from the tree. And then the next model actually tries to predict the residual. And then it finds the error left after that residual is predicted. And then it takes that extra error, then it fits another decision tree on that residual. And it goes through until you get to your end decision tree here. So it makes the adjustments as you go to try to basically predict well the error it got wrong in the earlier decision trees. And it gets gradually better as you go. So the steps of a gradient boosted regressor. It finds the mean value of the target value in your data. This is our base prediction. So that would be finding, after fitting one decision tree model, it would find the values there. And then we calculate the residual for each observation. So the actuals minus the predicted value is what residual means. Then we'll multiply the residual by a learning rate, forcing the algorithm to make small incremental changes over a larger number of decision trees. That is one of the hyperparameters you can tweak in decision trees, is the learning rate. So it slows it down. It constructs a decision tree to predict the residual. And then if there are multiple residuals in one leaf, it finds the mean residual for the entire leaf, as we discussed. So finds that mean at the end. It then computes new residuals, actuals minus predicted, and then it goes on to the next. And it repeats steps 3 through 5 until the number of decision trees equals the number specified in the hyperparameter number of estimators. So remember that number of estimators, it's again a hyperparameter, and it will say if you do 300, it'll stop at 300. Are there any questions? So we have our base value here. In order to get our final prediction, it takes the base value plus the residual decision tree value plus the next residual to get our final predicted value. So it will be the mean calculated at step 1 plus the predicted residuals from all of the decision trees added together. So every single decision tree throughout, it adds on the predicted residual from those decision trees to get a final prediction. So what this is talking about is how we have to adjust the model if it's a classifier. So several adjustments have to be made. It's very similar to what you would see in the linear versus logistic regression. So the adjustments that we have to make, first, to obtain the base value, you have to find the log odds of the target feature. So if I went over the log odds in detail in the ridge and regression, the ridge regression and lasso regression class that I did, but it basically bounds it between 0 and 1. So now we have a probability score instead of like a predicted value that is continuous. So this equals, to obtain the base value, you find the log odds of the target feature. This equals the number of true values divided by the number of false values. And this value is converted to a probability using the logistic function. And then the residuals are calculated for each instance in the training data and multiplied by the learning rate, just the same. And a new decision tree is used to predict the residual value. When there's more than one prediction in a leaf, they uses this in order to find a single value from that leaf. So the sums of the residuals over the sum of the previous probability minus 1 minus the previous probability in this case. And the closer it is to 1, it takes the 1. If it's closer to 0, it has the predicted value of 0. Any questions? All right. So to make new predictions in a model, it uses the following formula for decision trees. It takes the base log odds plus the learning rate times the residual. So this first value that we get in our first decision tree plus our learning rate plus our error value. And then the logistic function is used to convert it from a prediction to a probability. So bounded between 0 and 1. So these are going to look mostly pretty similar to what you've seen in the past. Number of estimators we've already talked about. It is available in gradient boosted trees as well. The learning rate we've already talked about. It's how it slows down the training of your model. Subsample is when you take a fraction of your samples or your rows to train your models. Think similar to bagging again. When you do that, and when it's less than 100% of your samples, it's then called stochastic gradient boosting. I find it doesn't work very well. I've never ended up using it in my final model. The loss function is how to optimize when data is split. So impurity versus the Gini impurity versus basically the different functions that you use to know how to split your decision trees. If you look up and earlier in these slides, I go over them, and in my decision tree class, I went over that in detail. Tolerance for early stopping. So if the loss function did not improve by the tolerance that you get, by at least the tolerance that you specify, or there is no change, then it cuts off and does early stopping in that case. We can do the number of iterations with no change. So if the loss function hasn't changed for 3 iterations, for instance, and we set it as 3, it would stop the model. And then you can also do the validation fraction. So a proportion of training data used as validation set for early stopping. So if you set the tolerance or the number of iterations, it will use that validation data set to choose that early stopping area that you would go. So the larger the fraction that you choose, the more accurate the early stop will be. It's coming back in here. Quite a lot of trees in here. Okay, GBT. Find the top one, number of estimators. Okay, here we go. So here you're going to see that this looks very similar. The syntax is basically the same in this case, but we're using a gradient boosted classifier instead. We're going through our base model does better than the base model did for random forest, but it's not very different. Please keep in mind here that I'm using a small fraction of the original data set. It's tiny. It's like 200,000 out of, I don't know, 4 million. That's for the purposes that you can run this without having to wait for hours and hours on end. So in this case, 72% accuracy. Given how little data I use, that's actually pretty impressive. In this case, we use the number of estimators. So the number of trees that you trained went through, and it trained with 50, 100, 150, 200, and 300. So just like last time, it had somewhat of an effect, but not a big one, the number of estimators. And the time that it took to train with 300 was so much that you always have to do training time versus accuracy, and how much accuracy did we get for the continued training time. Max depth, we've talked about this already, so making it so it can only have a max number of levels. This one usually makes a pretty big difference. So you can see it's going up, it hits the peak of 73 accuracy at 9, and then it goes back down. And I set the number of estimators here because it was sufficiently high at 100 and I didn't want to take more time to train. So 73 is our highest in this case. The learning rate, I varied that between 0.05 to 0.35. This also had a decently good effect, and I would have kept going and done more models in a real life situation because it was still getting better in this case. But this is an example. So this would be a case where you would actually make the learning rate bigger and train more models to see how it helped in a like work situation where it wasn't just for a class. So the learning rate and the max depth seem to make the biggest impact on the accuracy. So, and the F1 score. So I wanted to try both of them at the same time. So I did the learning rate and the max depth, trained on multiple models. Now you can see down here, we start off 70, the accuracy is 72.4. It's getting 72.4% correct. It's going up, up, and up until it hits that 9 with a learning rate of 0.05. So we're hitting our best model right here. And then it starts diving again. So we hit our top of our bell curve here. This would be the minimum impurity decrease here. So we set 0.25, 0.5, 0.1. This one, it doesn't change it much. It's not really effectively tuning my model. Finally, I do max depth and max features. So setting max features to 7, 10, and 15. The max depths that seemed to do best in the previous models were 7 and 9, so I carried them through. and went through even using these, I got a better result in my earlier model. So it doesn't look like this is our best two hyperparameters to use. And finally, I tried stochastic gradient boosting. So taking a subsample of my rows, accuracy went pretty low. And so we wouldn't have wanted to use the stochastic gradient boosting in this particular case. It made my model really bad. If you look at the recall, it's dreadful over here. So we're not predicting zeros well at all. So that is a high-level overview of stochastic gradient boosting. Gradient boosted trees. This is a lot of information. So something that I did recently was actually add suggested reading to my website. So I obviously haven't posted this yet because I'm just doing it now. But you'll notice when you come down here for each class, this it wasn't there before. There's a couple books that I tend to like. So I came down, found the chapters. This is your best introductory chapter. Do not pay attention to the R code in this book because it's terrible. In general, do not pay attention to the code in this book. Python machine learning is a little bit harder. And I gave the chapter there. This is for decision trees. And then I also did, I have not actually read this one, but I've gotten good reviews on it. I've heard it's good. So I did that as a third one. The way I would usually learn this is I'd go through, read this one, which is very high level. Once I got a good grasp on that, I would move on to the Python machine learning. If I understood that pretty well, then I would maybe stop. If there were certain aspects that I was still confused about, then I would either read another chapter if I'm still really confused. And if I was confused about a specific topic, I would find a website about it usually. So if I didn't understand impurity and judging splits, if that was the part I was confused about, which usually would be in decision trees, I would go and read something on calculating impurity. So every class that I do, I'm going to add the suggested reading. So if there are certain parts that you didn't understand from what I was talking through today, you'll be able to go in and and read some of these. In general, it's going to be the same books every time though. And if you go into information and resources, websites for studying machine learning, every time I find a good website, I stick it in here. So tree methods, Ensemble, decision trees, random forest, gradient boosted trees. Also goes into XGBoost if you're interested. So this is sectioned out by model. So if you're confused about something, you can come in here and look as well. So those resources are there for you if you get confused. So are there any more questions before we log off?
Kelsey, one question, if you don't mind. You mentioned at the beginning of class that you use gradient boosted trees in feature selection. That's actually something that a coworker of mine and a customer of ours have been arguing about recently. Is that data dependent? I guess I'll just ask, because their data can be highly correlated and yet they're still just throwing it into gradient boosted trees. And she says that's a terrible idea, but I just wanted to see if that maybe explains why you said you can use it, but maybe data dependent.
So that's why I usually use 3 to 4 models to do feature selection in general, because they're all every data is different. And each of the models is going to catch something different than the other ones. So I usually use random forest and gradient boosted trees. In general, you're going to see different results for those on feature selection. And then I throw in lasso regression almost always as well for feature selection. So then you can think of it as in a survey going and talking to more people. We have 3 different models that do 3 different things. And then if one shows up more often than if it shows up in 2 of the models but not in the other, we know it's still important. So then we move it on. The one thing about gradient boosted trees that is helpful. So when you have, you're talking about multicollinearity in that particular case. So in XGBoost and gradient boosted trees, when 2 features are highly correlated with one another, and so say you, for instance, had, let's see, it would be, I'm blanking. So say you had income and median household income and education in your model. They're going to be highly correlated with one another because usually higher education is correlated with median household income.
Well, if you want an even stronger example, in our case, things like number of households and population.
Yes. So that's another example. So in gradient boosted trees, when 2 things are highly correlated, it finds the one that's better and drops the other one out. It drops it down to almost nothing, almost always. So it usually penalizes the highly correlated variable and it drops close to nothing. So now if you do a lasso regression, it's not going to do that. So you're getting 2 different perspectives from that, in 2 different ways to do that feature selection. And if you can use SHAP values, you should. But in some cases, the data is too big and there's not a good way to parallelize SHAP values. So sometimes you're just stuck. Does that make sense?
Yep, that makes perfect sense. Thank you.
Mm-hmm. The gold standard is Shapley values in every case. I agree, the best way to do it, but when you have 8 million rows and you're using and paying for like $20 an hour for your compute, you're not going to want to do that because it'll just sit there for 5 hours at a time for each model. Yeah. Any other questions? Oh, thanks. So keep in mind, everyone. Yes. Looks like there's a job. Somebody is looking for has a position open as well. And it's good. You want to pursue ML. So, yep, feel free, guys, to email me, kelsey.mnet@gmail.com if you have any questions. I may not get to it right away, but I will answer you eventually. So please feel free to do that. And I hope you have a great evening.
Hey, Kelsey, there's one more thing in the chat specifically for you. Just wanted you to see it before you dropped.
Hi, Kelsey. At the beginning, you were talking about the new job opportunity at Merit's, the junior data scientist. I couldn't find it on the website. Can you help me locate it? It may actually not be called junior. I'm going to actually stop the recording. And then I